May I start? So our seminar will go together with lecture. So it will be seminar 9 plus the continuation of the lecture. We will continue our classification of phase diagrams and we will consider examples. So now it's time for an example. So I need to illustrate the case when we have a saddle, right? So it is task number 2. Now our equation will be given in the form 2x plus y over 3x plus 4y. So consider this differential equation. And we want to construct the integral curve. It is in R2. But if we introduce time, and if we consider parametric functions given parametrically, so as a function of t and x is a function of t, then dy over dx can be written as y prime with respect to t over x prime with respect to t. And this equation can be rewritten as y prime with respect to t. So let's start with x, I think. So it is equal to 2x plus y over 3x plus 4y. And we can rewrite this as the system of equations. X prime is equal to 3x plus 4y. Y prime is equal to 2x plus y. And we can consider this system as the system of autonomous equations. So their right-hand parts do not depend on t. And these are derivatives with respect to t. And so we are now in the case of the of our theory, and we want to solve this, and we want to obtain the qualitative figure, the qualitative structure of phase trajectories. To do this, we should start with the characteristic equation: 3 minus lambda 4 2 1 minus lambda equals lambda squared minus 4 lambda plus 3 minus 8, lambda squared minus 4 lambda minus 5. And the roots are lambda 1, so by the Wyatt theorem, the roots will be 5 and negative 1. Right, so we start with this differential equation. Here we have dy over dx. But the analysis of this equation is rather difficult, right? To simplify, we will introduce the new parameter t and rewrite this equation as the system of two autonomous equations. And now we will try to analyze the phase space, phase trajectories of this system of equations, and this will give us the integral curves for this equation.
So this y prime in the parametric form.
Right. With respect to t.
It's different from the one you first proved.
Is different from what?
From the y prime with respect to x.
Right. So we know this formula. So if we have the parametric functions, if y depends on t, x depends on t also, then we know that the derivative y with respect to x is equal to the ratio y, the derivative of y with respect to t, over the derivative of x with respect to t. So this was studied on the first course, right? In the first semester, or maybe second semester in your case. but I will use this. Well, so these are eigenvalues. They are different and have different signs, right? And then, okay, next we need to know the eigenvectors. Let's find the eigenvectors. First, so if we take lambda 1, then we substituted here 3 minus 5 is negative 2, 4. 2, negative 4. So we can take, so as the eigenvector, we can take the vector 2, 1. So it satisfies this equation, right? It is easy to guess the vector, right? This is a solution, eigenvector. Lambda 2 is equal to negative 1. Then we are trying to solve, so 4, 4, 2, 2. So the eigenvector is 1, negative 1. So we are done. Now we try to, so we need to draw the lines through these eigenvectors. So the first line must go through the vector 2, 1. So these are axes. This is an equilibrium point. So x equals 0 is an equilibrium point. Then the vector 2, 1 is this. This is 2, 1. This is the line through V1, determined by V1. And the line determined by V2 is, so 1, negative 1. 1, negative 1, it's here. So it's this line. I do not indicate the directions now, right? So these are two lines. Then the directions will be the directions of the phase trajectories, phase trajectories. So we must write the solution. So xy is equal to c1 multiplied by e to 5t, and the vector is 2, 1 plus c2 e to the power negative t times 1, negative 1. Let's analyze the behavior of the trajectories. So first, st, okay, let's start. So I will repeat some information for Kathy. I think if we start with a point on the line through V1, for example, from this point, what will be the behavior? So we want to know the behavior of the trajectory as t approaches positive infinity or negative infinity. So first of all, if we start with a point at the line through V1, then c2 is 0, and we will remain on this line, right? Because it will be, so the solution will be given by just first component. This will be 0. So we want this vector. If for t equals 0, we get a point here, then this means that c2 is 0. Of course, it can be solved, right? So if we equate, so we can solve this explicitly and prove that c2 is 0. So it is not difficult to show. Then if t approaches positive infinity, what will happen? We will go away from the origin. for if C1 is positive, we will go in this way, and if C1 is negative, we will go this way. So the direction of motion along this trajectory will be away from the origin, because 5 is greater than 0. Right? And we indicate the direction using the arrow away from the origin. Next, if we start with a point on the line through V2, then C1 is 0. And if t approaches positive infinity, then e is raised to the power negative t, so negative power. If t approaches positive infinity, then this will approach 0, and so we will go toward the origin. So the direction will be toward the origin. And after this, we will continue construction of our phase. So phase trajectories in this way. So the form of the trajectories will be described before in general case, but now this is only an example. And so we will just draw something like this. So the answer for this task is this figure, right? Qualitative behavior of phase trajectories. Now move further. Let's consider the case of equal eigenvalues, equal real eigenvalues. And real. So suppose they're equal to lambda. There are two subcases. So in case 3.1, we have two linearly independent eigenvectors associated with this repeated eigenvalue. So two linearly independent V1 and V2. And the solution can be written as C1 e to the power lambda t V1 plus C2 e to the power lambda t V2. Or it can be written as e to the power lambda t C1 V1 plus C2 V2. So let's draw a figure. So we have an equilibrium point. This is the origin. The origin. So this is the origin. So suppose we start from some point which is outside, so which do not coincide with the origin. It doesn't, no, which doesn't coincide with the origin. So from some point. So C1 and C2 are fixed, and so this vector is fixed, right? Then this vector is fixed by the starting point. We fix. So if we have a starting point, then we fix C1 and C2. So this vector, it is fixed, and it is multiplied by some coefficient. Well, and so we will move along the line through the origin and this given point. We will remain on the line through this point and the origin. But if lambda is greater than 0, we will move away the origin. And if lambda 2, so this is for lambda 1 greater than 0, and if lambda is less than 0, then we have the following figure. So this is sink, this is source, and they are called so proper node or star points. So it's better for me, star point. So they look like a star. Or it is a proper node. So now let's discuss the case of repeated eigenvalue and only one eigenvector, so a Jordan cell. Right? This is the most difficult case of a Jordan cell. Or maybe first of all, maybe let's. I'm trying to give an example. Let's consider an example related to this case number 3. So an example number 3 will be the system of the form x prime is equal to 2x, y prime equals 2y. The first step is the characteristic equation 2 minus lambda 0, 0, 2 minus lambda equals 2 minus lambda squared. So lambda equals 2 is a repeated eigenvalue. Now we are trying to find the eigenvector. So we need to solve the following. And we have 2 linearly independent eigenvectors. So any eigenvector is an any vector is an eigenvector. So the basis of eigenvectors will be V1 and V2. Okay, both listeners are sleeping. So sorry for awakening you. Okay. Well, and now the solution will be x equals c1 e to the power 2t 1 0 plus c2 e to the power 2t 0 1, and so it is e to the power 2t times c1 1 0 plus c2 0 1. And it is a source and a star point. Okay, now subcase number 3(2), when we have a repeated eigenvalue and only one eigenvector. And as a unique, linearly independent eigenvector. So this means that we have a Jordan cell and Jordan chain a minus lambda I times v1 times v1 is 0, and a minus lambda I times v2 is equal to v1. And in this case, the answer is given by p1 e to the power lambda t v1 plus v2 e to the power lambda t v1 plus v2. Okay, but I didn't give the detailed study of this case, so we'll only maybe touch this, right? But I don't want to go into detailed study of this case, so it is more advanced thing, but I need to mention this in our classification, right? Because this is a classification, it must be complete, right? So we need to consider maybe some to speak about this case. So it exists, so this situation may happen, right? So I can't avoid this because this is a part of classification. So in this case, so we have a unique eigenvector, right? If lambda is less than 0, for example, lambda is less than 0, then if we start on the line through v1, this is the line determined by v1, we will go toward the origin. Well, and if we start from point away from outside of this line, so then the motion will be so all the other trajectories will be tangent. So it will be something like this. So all the trajectories will be tangent to this straight line, right? And and it is called an improper node, So I will have a look. Or degenerate node, improper or degenerate node. So I will not give examples concerned with this case because we didn't discuss the solution. So we did not study this case in detail during when we tried to solve linear systems. So you should be aware. So you should be aware of this case. So you should know that it exists, but we will move further. Right? Let's move further. Next, we will consider complex eigenvalues. So case number 4 was about complex eigenvectors, eigenvalues. Sorry. Okay. Suppose so. Then, if the eigenvalues are complex, then they are complex conjugate, right? A plus or minus bi, where b, let b be positive. So then eigenvalues can be written in the form a plus or minus bi. And after the change of variables, linear change of variables, our linear system, like this, right, can be reduced to the following form: x prime equals ax plus by, and y prime equals minus bx plus ay. after a change of variables, our system can be reduced to this. And now we will try to visualize the phase trajectories in this case. How to do this? The best way to analyze this case is to introduce polar coordinates, right? Let's rewrite this system, this linear system, in polar coordinates r and theta. There were tasks about the rewriting equations in terms of polar coordinates, as you remember. So x is equal to r cos theta, y is r sine theta. Let's try to rewrite the system in terms of r and theta. Right, let's do this. To do this, we will differentiate this system, right? X prime equals r prime cos theta plus r minus r sine theta. Theta prime. And y prime equals r prime sine theta plus r cos theta sine theta prime. And from the other hand, we know from this linear system, we know that this is equal to ax, so this means that it is ar cos theta plus br sine theta, and this is minus br cos theta plus ar sine theta. And now we want to eliminate theta prime first and r prime then. To eliminate theta prime, I want to multiply the first equation by cos theta and the second one by sine theta and add the equations together. This will eliminate these terms. Right? These terms will be eliminated. But the first terms will be r prime times cos squared theta plus sine squared theta equals, so it is 1, of course, right? This is 1. So we must multiply this by cos theta and this by sine theta, and we will get, so, and add them together. So we will get, so b will be eliminated. So these terms will be eliminated, right? Is it clear that these terms will be eliminated by this operation, by using this operation with plus and minus, right? And what about these terms? It will be ar times, and that's all, times 1. So the first equation will be r prime equals ar. So very good, right? This. What about theta prime? Let's find theta prime. To obtain theta prime, so maybe I will rewrite it somewhere. I will rewrite it here. To obtain theta prime, we will multiply the first equation by minus sine theta and the second one by cos theta. This operation, and add them together. This will eliminate r prime, and this will give us theta prime equals, so the terms with a will be eliminated then, and this will be minus b r, right? Minus and times r, right? So r times theta prime minus br. So we have the following. The second equation will be theta prime equals minus b. Very easy. So this system of equations can easily be solved. Let's solve it. R is equal to C, let it be C1, e to the power at exponential function, and theta is equal to minus bt plus C2. These are two constants, C1 and C2. And now let's try to draw a figure, to sketch the figure. So we have no eigenvector. All eigenvectors are complex, and so we can't draw them using a plane, real plane. But we can illustrate this. Right? So, and these are axes. Let's try to illustrate this. So this is the equilibrium point. So suppose first that A is, say, less than 0. If A is less than 0. And B, let B be greater than 0. In this case. Then C1 must be positive, of course. 0. What happens? If t approaches positive infinity, then this is right, exponential decreasing with the exponential speed, right? So r approaches, and what about theta? Minus bt. So this means that theta changes to b is positive and theta is negative. So it moves clockwise, right? So if r is constant, if r were constant, right, then we move along the circle in this way, right? The motion will be around the circle. But since r is decreasing exponentially, then we have something like, it's a spiral. It is called the logarithmic spiral. So and this is this will be, so this is sink, of course. It is called the spiral sink. For A, if A is less than 0. But if A is greater than 0, then we will have a spiral source. It will look like this, spiral source. Okay, and maybe we may discuss case number 5. Case 5. So in case number 4, A is not 0. But case 5, when A equals 0, should be treated separately. If A is 0, then we can proceed in the same way and obtain the further. Okay, let's use the same formulas. So the same formulas can be used for analyzing the situation, right? This the same formulas, only for A equals 0. And if A is 0, then R is constant, right? So R is So r prime is 0 and theta prime is minus b. And so this means that r is constant and theta is equal to minus bt plus c2. And this means that we have so our orbits are closed circles. But the direction can be arbitrary, so we can't determine the direction from in general case. So it depends on the situation. So it should be analyzed in each particular case, right? The direction of motion around this circle, right? So the name of this case, is a center. It is called a center. So spiral source and the center. Well, and now let's discuss an example. For for case 4 and for case 5, we may consider different examples. Yes, of course, sure. For one of these cases. So the space is here. And now let's consider the following. Y prime equals 4x minus 3y over x minus 2y. So first we should introduce the new parameter t and rewrite this equation as a system of two equations. Correct. And the matrix should be in reverse, so we should reverse the order of these two. So we should start with x, write x and x. So if you start with the variable x, so you should switch these two equations. You can rewrite, not remove, but you may rewrite this in the form x minus 2y and y is 4x minus 3y. Right, prime, right. Coffee. Wake up. He's sleeping. Coffee. Look at the water. I think you are very tired because of the preparation to the exam. Physics, yes? I think so. I think it's not easy. Yes. Is it the state exam or not state exam? I think this the easiest. Maybe. I'm trying to make it easy. Wow. Because each time I'm looking at you, and I stop myself when I see that it is difficult for you. I know that our courses are not easy, but I'm trying to adopt them. Okay, 1 minus lambda minus 2 for plus 2. I think so. I will check. Correct. This is correct.
So no,
Yes. So, yes, it is possible to continue this way. So this is a spiral. So A is negative. So it is a sink. B. So we needn't know. It is always plus or minus. So B, we
can determine.
right. We cannot determine, of course. So it is always positive, right? Because it is always plus or minus something positive here. So we can determine only the sign of A. So if A is negative, then it is sink, right? It is sink. But the direction of the spiral cannot be determined only from this. So it can be in two ways. It can be in this way, or it can be in this way. And so we can't determine the direction of rotation only from this information. So the best way to determine this, right, is to construct some tangent vector. And at one point maybe. And this vector will show us the direction of rotation. So it can be done, for example, in this following way. So these are axes without direction. So let's take, so this is the equilibrium point. Let's consider one point, maybe, so suppose this. Let's consider point 1, 0. And compute the velocity vector at this point, right? So look here. So at this point, if we substitute 1 and 0 for x and y, we will get, so at this point, x prime is equal to 1, and y prime is equal to 4. So it's this vector. 1 and 4, it looks like this. So this vector shows us the direction of rotation. It must be in this way. We must follow the vector. And it will this will be an ellipse, not a circle, right? Because we have started. So this system of linear equations is obtained after some linear change of variables. If we make a change of variable, then this change of variables make a circle. Turn the circle into an ellipse, right? And so it may be an ellipse, not a circle, and this is the direction of motion. Like so, our orbits must be tangent to this vector, and then this way. So the rotation is done in this way.
In which case will it be a circle?
Now, so it depends on the linear change of variables. So I think we will not discuss. So it's not an easy problem. So we should find this exact change of variables. This is not an easy task. It can be done using the machinery studied in linear algebra. So how to choose the linear transformation, and then we must so analyze. We need to do this. So this is qualitative portrait, of course. So the most important thing here is to determine whether it is a spiral sink or source. This is the first question we need to answer. And the second question is the direction of rotation. So this is the second important thing. But circle or ellipse, it doesn't matter in this case. So this is a qualitative picture, right? Now let's move further. So the next example. Kathy, do you want or not? Not because you are sleeping during the right. So it will be x prime equals minus 2x minus 5y, and y prime is 2x plus 2y. Let's analyze this face portrait. No. Plus, well. I times I. So the roots are purely imaginary. This means that it is not a spiral sink, so neither spiral sink nor spiral source, but it is a center, right? Center. It will be a center. So you need not do this. This is for theoretical analysis. But you know that the orbits will be ellipses around the origin. Right? But you must determine the direction of motion along this orbit. So this will be orbits. The direction clockwise or counterclockwise. Right. So you should take some point, maybe 1, 1, 0, for example, 1 minus 1, right? It's here, right?
Y prime is equal to 0.
Right. So it is a horizontal direction. So this way, right? So it is the horizontal vector, right? So from this point, and it must be tangent to maybe, or maybe we will rewrite. Yes, I think it's ellipse. Yes. And direction is in this direction. We'll try to. So this direction. So here we have x prime is 3 and y prime is 0. So this vector. And so we have an ellipse, and it is tangent to this line, right? And the rotation is in this direction, I think. Like I think something like this. So this ellipse and rotation in this direction.
Orbit of
orbits. So this is the face portrait. Thank you. Well done. Yes. And so the last task for today. And after this, we will finish. You want to complete? So x minus 4y and 2y minus 3x. Let's solve this. Okay. This can be any of cases studied before. It may be nodal sink, nodal source, saddle point, right? Saddle, or spiral source, spiral sink, and so on. Right. Uh-huh. All right, right. I think this. Uh-huh.
I can't guess the solution.
All right, of course. -2 and -5, yes. I usually start I start with this term. So the product. So if the integer, the product must be 10, and so only 1 times 10 or 2 times 5. So 2 and 5.
I usually just look at 1.
Right.
If I don't see 1.
Okay, so 2 and 5.
Okay. Lambda must be -2 minus. So that's yes. I think so we have to change the
Right. So different real and both negative. So for saddle, we have two different signs, right? And the same sign is for the first case. First, so right, nodal source or nodal sink. Depends on. So nodal, and since they are negative, it is sink, nodal sink. So we need right. We need eigenvectors. Yes. Just yes. So switch. Right. Correct. V1 is this.
Do I need to write what is in the bottom? I can just say 1 minus.
All right, so we did not know, right? So 2 and 2 is enough, of course. It is enough. Only to check yourself if maybe, right, maybe this is not eigenvalue, so maybe you made a mistake in finding the eigenvalues, and so this is only to check yourself. But the first row is enough, of course. So 2 vectors, 2, 1, and 1, negative 1. And 2, 1. This, right? Okay, so they will be orbits, of course. So it may be a solid line, right? But without direction first. So draw a solid line, right? Right. So this direction is determined by this, right? It is v2, right? v2 and v1. Well, then the directions minus and minus to the origin, right? To the origin. Toward the origin. Right, in this direction, correct. And the same thing. And now, at last, we need to determine which line the trajectories will approach. Right, they will approach lines. Which line? So you must determine which term is dominant as t approaches positive infinity. I think this term is dominant because negative 2 is less than, so it is right. It is greater, right? It is greater than this. So if we compare these two coefficients, right? So this is greater than this as t approaches positive infinity. Then this term is dominant. But when I make an analysis, I did the following. So to prove that this is dominant, we can rewrite this solution in the form C1 times 2, 1 plus C2 times e to the power negative 3t times 1, negative 1. And here we see that as t approaches positive infinity, so this approaches a 0 vector. And our solution approaches this line determined by 2, 1. 2, 1 is this, right? So our trajectories will touch this straight line, and they will behave as follows. And at negative infinity, this term will be dominant, and so they, so the direction will be close to this vector, right? Parallel, almost parallel, maybe. Thank you. Okay, so that's all. So we may start. We may finish here, right? That's all I want to discuss today. Thank you for your attention.